usually like know that you know what you're doing, but if you don't explain it thoroughly, you lose like kind of silly marks there.
Yeah. And in a 24-hour test too, right? You have hopefully the time where you're not like scrambling too much. Yeah, I don't know. I don't know yet if we're going to have the 24-hour one.
I don't think, I don't know. It would be unprecedented at least because they haven't done 24-hour test exams yet.
Yeah.
Never heard of one at least.
Yeah, I don't know, Karina. I really don't know. It'll come down to it. In theory, because it's instructor administered, we could, as long as we get permission to do it, that data could change up until the last day of classes, in the sense that like, they could publish a schedule and then we appeal it, and up until like the last day of classes, that could actually change. But, I'll let you know once I have something I can talk about. Yeah, that is a little bit different. So the rules for a take-home final are that you have to get the final exam usually on the first day of class, and then it's due in your normal exam period. So we do have, I have take-home finals in other math classes, totally. But there are a couple of rules. So one, they usually don't like take-home finals in post classes, like classes that will actually make a difference to your post results. So generally, other departments are usually really against that. They don't like that. And then first year classes, not so much either, right? Like as you get into higher years, that becomes higher years and smaller classes, that becomes a little bit more okay. But yeah, especially like first year math is typically, that's not the case. So this week, we're going to start off, we're doing chain rule and like implicit differentiation. I'm pretty sure it's implicit differentiation. So we're going to start off with a chain rule question. We're just talking about life, talking about like the final exam and if it would be hard. And you didn't miss anything, Ahmed. Like I didn't reveal any secret information about the final or anything, so don't worry about it. But yeah, so we're going to start off with a quote unquote straightforward. It's straightforward in the sense that it's just a computation, like there isn't something subtle going on here. That being said, it's a little bit of a tricky question, right? Because the function's a little bit gross. So it could take you a little bit. Don't hesitate to take some time to try and do this question. No, Riri, for sure we're online. The question was whether or not it'll be like a 3-hour test or a 24-hour test. But we're online for sure. We have an online final. Yeah, we'll see. Yeah, we don't know. Would you guys prefer a 3-hour final, or would you prefer 24-hour? I mean, it might depend on what your exam schedule is like, right? Because what if you have other exams in that 24-hour window? Okay, so the class is pretty, based off of the 6 votes that I've gotten, the class is unanimous. So, okay, I'll push for a 24-hour exam then. Yeah, the exam is cumulative, Namir. You don't want to, because the final exam has to be a certain weighting. I can't make like a 10% final. That's actually prohibited. So you don't want a 40% exam that's only on the last stuff that we did. Not that the last stuff we did is hard, but it's like, you don't want that to be 40% of the mark. How long would it be? It'd be like 5 or 6 questions. It wouldn't be that much longer than a normal test. Yeah, it'd basically sort of be like one question from every unit. So like a financial math question, linear algebra, a probability and counting question, derivative calc, integral calc, and multivariate calc, right? Yeah, could be. Okay, I'm gonna lock this one down in 30 seconds. So see if y'all can get your answers in. Okay, that's an interesting approach. I mean, obviously, if it was a 3-hour exam, we'd be a lot more lenient in presentation, right? Because obviously you don't have the same amount of time. So, we would be more lenient in that regard for sure. We'll make expectations about that sort of thing clear. So if it does end up being a 3-hour exam, we'll announce that, hey, listen, we know you haven't done a 3-hour exam in this class before. We are going to be a little bit more lenient. It doesn't mean you get to be garbage, right? You don't just get to write down crap on your page and hope it gets marked correctly. But, if you're going through it a little bit quicker, we won't be as, anal about these sorts of things. That's the idea. Okay. So let's see what we got here. The class is leaning towards A, but only half the people answered. So I don't know what's going on there. Then again, if you're sitting in a hallway, it might actually be a little bit tough for you to do some math, but hopefully you found a place where you can, write stuff down and work on it. A is the correct answer. Absolutely. So let's see it. And of course, there's different ways of writing this down, but let's work on that and see if we can't get the right answer here. Did I close that? I guess I did. Well, Ahmed, yeah, let's hope so too. I hope you did well. Okay, so we've got the function. We're asked to find the derivative, right? So this is question 1. Believe it or not, we actually started on question 1 today. So it said find, d dx, x plus root x. Okay, and obviously the actual question was stated a little bit differently, but this is effectively what we wanted to do. Now, if you're having a little bit of trouble, so this is a chain rule problem because we've got this composition of functions. If you're having trouble seeing like the order that you should do things, I strongly recommend that you actually break the problem down into its constituent functions. Okay, just make your life a little bit easier like that. If you're one of those people who do it in your head, by all means, go ahead and do it that way. So I am going to break it down into its component pieces though. So what I'm going to do is I'm going to define g of x to be the square root of x and h of x to be x plus root x. And that this way, if I compute g of h of x, that's the function that we want to differentiate, right? So we want to differentiate the composition of g and h. Okay, so by the chain rule, we're going to get okay, so it's the derivative of the outside, right? And then we evaluate at the inside. And then we multiply by the derivative of the inside. So we need to figure out what g prime and h prime are because they do show up in these equations, right? So let's find the derivatives. Whoa. So finding the derivatives. Okay, so we're going to get g prime of x is 1 over 2 root x. Let's stop there, make sure everyone's okay. Because I think I saw a Piazza question where someone might have been struggling with this. So I want to make sure everyone's okay with this one. And if not, we can talk about it. But is everyone okay with the fact that the derivative of this function is this thing? Is everyone okay with that? Yeah, absolutely. Yeah, absolutely, Curdy. Okay. So I got a couple of people asking how. So to do this, maybe let's kind of break this down into steps. So this is the same thing as the derivative of the square root of x. Okay, yeah, let's do it. So it's the derivative of the square root of x. I haven't done anything, right? I just put the derivative sign in front. And now what I want to do is I'm just going to write the square root as x to the power of a half, right? And the reason that I do that is because now I can use the power rule, right? If I have x to the power of a number, I can use the power rule. The power rule says bring the number down and subtract 1 from the exponent like that. All right, so we get 1/2 x to the negative a half. And if you wanted to stop there, you absolutely could. Alternatively, if you just want, like, I don't like fractional exponents. I kind of prefer to get rid of them. Sometimes they're okay, but so if I rewrite this, so it'd be 1 over x to the 1/2, right? That's what happens when you have a negative exponent, it means you take 1 over. And then again, x to the 1/2 is square root of x, right? like that. Okay, so we use the power rule to do this. I use the power rule right, where did I use it? Right here, right? That's the power rule. And then the rest of it after that is just kind of like rewriting it in a nice way. Okay, so is everyone's okay with that then? Cool. So you canceled out the fraction exponent by square rooting the x. I didn't cancel anything, right? So remember, the derivative of x to the power of a is axa to the minus 1, right? This is the power rule right here. So what I did here is that a is a half, right? So you pull the half down and then you subtract 1 from it. So there's no cancellation going on. All I'm doing is I'm applying that rule above in order to be able to differentiate this function. Right, and in fact, we still do have a fraction in the exponent. All I did though, it's not that I canceled, it's that x to the 1/2 is the square root of x. Maybe that's what you're asking, right? X to the 1/2 and the square root of x, those are the same thing. Right, and that's important because that will really help us to be able to differentiate things. Yeah, okay. Now, h of x is very similar. So h prime of x, right? So that's the derivative of x plus root x. And then we know, yeah, sure. Well, we're getting to integrals. We're getting there, but we're not there yet. So we know that if we differentiate this, we just have to differentiate x and then add it to the derivative of root x, right? We can do them separately and add them together. So we get this, right? And we don't have to redo the work for root x. We already did it above, so we can just use that. So here are our derivatives. And now I'm going to take them and I'm going to plug them in to this expression here, okay? So we're going to get the derivative of the square root of x plus the square root of x. So what did we say? We said that was g prime h of x times h prime of x, right? Let's plug everything in. So g prime is 1/2 times the square root, and then we plug in h of x into that, right? And then we do h times h prime, so 1 plus 1/2 root x. Yeah, exactly. Yeah, this is the chain rule formula. Right here. So this is chain rule. Okay. And all right, we need to do a little bit more because I actually have to put h of x in, right? So if I do that, I'm going to get 1 divided by 2 root x plus root x times 1 plus 1/2 root x. Okay, and a lot of the times you'd be done here. I would say you don't really need to do any more sophisticated simplification other than this. Now, that being said, though, the problem does ask you, like this doesn't seem to be any of the answers, right? So we have to do a little bit more work than that just to get one of our multiple choice answers. So what I'm going to do is in the square brackets, I'm going to give that thing a common denominator. So that'll give me 2 root x plus 1 all over 2 root x. And so that is going to be 2 root x plus 1 divided by, this is nasty. Okay, so this is going to be 4 root x times root x plus root x, right? And yeah, okay, so this is almost looks like the answer. So the answer just though combined these square roots. So that was 2 root x plus 1 divided by 4 times the square root of x squared plus x root x. And that should have been a. Yep, so that was a, like that. Same note, nothing too big. We're just doing problem 1 from the thing, which I'll show you in a second here. I'm a bit confused on how you set up 1/2 square root of x. Okay, sure. Like this part right here. Okay, so I have a student who's just like, oh yeah, I don't know what happened here. Okay, so in that step, that's me doing this. Okay, so that's this bubble right here. So if we go up, let's look at g prime of x, right? G prime of x is 1/2 root x, right? So g prime of x is 1/2 times the square root of x. So when I plug h of x into it, then everywhere I see an x, I'm just going to put an h of x. Oh, sorry, this should be g prime h of x. Yeah, no problem. Okay, and can you recap the last step denominator? Sure. So this step, I assume, is what's being asked, like this equals. So what I'm using here is the fact that the square root of a times the square root of b is equal to the square root of a times b, right? Like the multiplication just works out. You can actually smush things together under the square root sign. So if I look at this denominator, I have square root of x times the square root of x plus the square root of x. That just means that I can basically write it under a single, right? Yeah, okay, you got it, right? So I can write it under a single square root, and that's why it becomes the way it is. Okay, everyone else is good? Okay, sure. So specifically, what is bothering you about the final answer? Like, do you see how we got it? Specifically the x, oh, I see. Okay. So root x plus x root, or sorry, plus root x. Okay, so now I'm just going to write everything under a common square root sign. Like that, right? And that is, if you expand that out, that is that. Does that help? Okay. All right, right on. So that's a good one. All right, now this next question that we're going to do, so Simon, you came in a little bit late, so I'm just going to, I'll show you the question really, really quickly, but I need to go to the next one. Okay, so it's just this one. If you snap a picture of it really, really quick or take a screenshot or something, you'll get it. Now, the next one I don't want to spend too much time on. It's super important, but why can't I scroll? That's weird. All right, so let's try this one. This gets used a whole lot. Okay, it gets used a whole lot everywhere. But like I said, we're not going to spend too much time on it. See if you can get it. Yes, yeah, derivative of ln x is 1/x. Yeah. Shanze, let me think. I don't think you can do it using only the power rule, but if you want to write something up and send it to me, you can. The problem is that it does have, like, it's got other stuff in it, right? It really is a function composition, and it's not obvious to me how you would do it using only the power rule, but if you have some sort of clever thing that I'm not thinking about, I'd love to see it. So yeah.
Was that for the previous question?
Yeah.
Yeah, I was trying to do it using power rule only, and I couldn't get anywhere.
Yeah, and the problem is that, like, it doesn't, right? You can't distribute across the addition.
Yeah, exactly.
I'm confused. Why do we use... It's just the logarithmic differentiation, which is the formula you mentioned in the reading. So Connie, are you asking, like, why are we even giving this as a question? Because I've explicitly mentioned this question? Yeah, that's true, but it's worth, I really want to reinforce the importance of this one, if that's sort of what you're asking. And it's true. I'm pretty sure. Yeah, exactly. And I did, yeah, this formula is explicitly in the reading. So we're going to see how many students did the reading. Maybe that's what this is a poll question of, right? Yeah, it's just a poll question of how many students did the reading. Okay, so I'm going to lock it down in like 20 seconds here. All right, so how many students did the reading? That's the question. And 13, maybe it's the 13 is the answer. I don't know, but so D is the correct answer. And it was kind of pointed out in a direct message that, yeah, with this I actually explicitly gave this formula in one of the readings questions. Yeah, that's okay. You know, if life takes up other things, that's one of the great reasons why this course is the way it is. One, it's recorded, and two, the lectures are online, you know, the videos are online. So if sometimes you got to take a break because you're doing other stuff, as long as you make sure you catch back up, it's not the end of the world, right? Just make sure though, you know, if you have to take a break from 133 to do management or whatever, that if anything doesn't make sense, you work hard and catch back up, right? But otherwise, totally, right? You can kind of do this stuff asynchronously, and I don't think that's an issue. Okay, so in this question, we're asked to determine the derivative of ln of a function. Okay, now, like I said, we're probably not going to spend too much time with this, but again, if there are some, like, you know, if you're having issues, don't hesitate to yell out and let me know. So when we do this, right, so we're going to first take the derivative of the outside function, which is, so let's say recall, maybe just let me put this on the side here. So let's say, like, recall that the derivative of ln x is just 1 over x, right? So when I differentiate ln of f of x, I'm going to get 1 over f of x, right? But then I have to multiply by the derivative of the inside, remember? Right? I have to multiply by f prime of x. And I get that. And that was answer D. Okay. So I think if there's going to be any confusion, it's probably from this part right here. But if not, if everyone's got that, then great, phenomenal, we can move on. But let me know if that's bugging you at all. But yeah, right, we're going to take 1 over, the derivative of ln is 1 over x. So we have to do 1 over f of x, right, derivative of the outside, but evaluated at the inside, times the derivative of the inside. And this is really, really nice because the derivative doesn't involve any logs, right? There's no logarithm anymore. And this is the whole point of logarithmic differentiation. This is probably where this is mentioned, the video this is mentioned in. And that's the power of logarithmic differentiation. Differentiating log gets rid of the log, right? The derivative of ln is 1 over x. Yeah. Right, that's the important part, right? So this is, in some sense, I don't like writing this because this is somehow mathematically blasphemous, but this is, you know, ln, the derivative of ln evaluated at f of x And the derivative of ln is 1 over x. So when we replace x with f of x, that's why we would get this, right? Don't do this. This is kind of bad form, right? I mean, people know what you're talking about if you do it. I don't like doing it. It's bad form. But again, you'd probably be okay. People would know what you mean. Why do we multiply by differentiation if it's in the denominator? So remember, the formula says that the derivative, let me use a different function name here, is h prime f of x times f prime of x, right? So we have to multiply by the derivative of the inner function when we do it. And Terrace, does that make sense for you too, right? Like why the f prime is there, right? So here, h of x is playing the role of ln x. F is just itself. Okay, cool. So the derivative of ln x is, so same, if you wanted to think about it like that, you're close. So it's not that the derivative of ln x, it would be 1 over x times the derivative of x. If you wanted to think about it like that, but you don't have to do it that way. Like that's just kind of like making it a little bit more complicated. But if you want to do it, that's fine. And then because, you know, this just ends up being 1. But yes, I mean, this is absolutely true. If you think of x as being its own inside function, absolutely you could do it this way. And it still does give you the right result, right? Curdy, no, yeah, that's not necessarily showing up in this question. What do you mean by the intuition for ln f of x? It's just, there isn't necessarily an intuition. The intuition for the derivative of ln x being 1 over x is a very exotic thing. It's actually quite difficult to do. You have to look at the example for it, like where I actually derive it, which is in the inverse. I'm pretty sure it's in the inverse function theorem video. But the fact that this is true comes from the fact that this is true, right? The fact that the derivative is equal to itself for the exponential, the derivative of e to the x is equal to e to the x, that's the thing that gives you the fact that ln x is 1 over x, right? And that's where that comes from. Intuitively, it's not at all clear, right? In fact, in math classes, when we do this in a math class, we do not define the derivative of ln x we don't actually define ln x to be the inverse of e to the x. We define ln x in a completely different way. Yeah. It's just one of these things that we do, you know, in like first year things. Here, let me just get the next question set up and then I'll kind of talk about that a bit. So some of you may have seen books that are called like early transcendentals, right? Like James Stewart's Calculus, early transcendentals, or Salas Hill and Ekin, early transcendentals, or Thomas, whatever the hell the other Thomas book is, early transcendentals. So what early transcendentals means is that exponential functions are talked about very, very early. And if you're doing a rigorous mathematics class, much like 137, you've actually got to, you can't do exponentiation. If you're doing calculus rigorously, you can't talk about exponentials until you've defined integrals. And we haven't even talked about integrals yet, right? So that's totally a thing. Yeah, John, I think John Stewart being a mathematician would be great, but of course there are way too many John Stewarts in the world, so we actually could be talking about different people. Brandon, what are you asking? Like, just like
I think it's just the lingo of this question, or like the way it looks tough, but it's not that bad actually.
Yeah. You just have to figure out what exactly this is. Shanze, I can't see HEIC files because they're only like, that's an Apple thing only.
Yeah. And, Tyler's against Apple, so.
Yeah, I love the Hermite polynomials are super cool. Like they come up in real life and they are super, super cool.
Do you remember, Tyler, do you remember the James Stewart calculus textbook that was used for this course before you changed it up?
It wasn't Stewart.
It was, wasn't it?
No, it was. I have a copy of it on my shelf. Where is that piece of garbage? There it is. All right, what's it called?
I thought it was a Stewart. Maybe that was MAT135. That was a Stewart, not 133.
Yeah, let me take a look. I'm going to turn my headphones off so I can't hear you. Hold on. Hausler, Paul, and Wood was the book. It was Hausler, Paul, and Wood. Yeah.
I thought it was the Stewart must have been the 135 then, because I remember there was a Stewart somewhere involved.
Yeah. Stewart for sure was like 135, 136. Yeah.
Okay.
Yeah, so these things for sure come up in real life. The person to really talk about this is Jordy, if you ever get a chance to bug him about this, because he's a bit of a, dynamical systems buff. And so these naturally appear in dynamical systems. Where this show up for me, and of course, none of you care, right? But where these show up for me is when you're characterizing the fine structure of the hydrogen atom, these things show up. So basically, you guys probably know, right? Hydrogen is this atom, and it has a neutron, a proton, and it has an electron, like a single electron, right? Hovering around it. And that model isn't actually very good. The electron is actually very much spread out. It looks more like a wave. And if you're trying to figure out what the waves look like and how the electron is spread out around the hydrogen atom, you use these Hermite polynomials in order to do that. So it's funny how these things show up, and they end up showing up very naturally. If you ask Jordy, though, he'll say something along the lines of, these form a natural orthogonal basis in the collection of, C infinity functions on the real line, or something along those lines. So they're mathematically interesting, they're physically interesting, they end up coming up a fair amount. So it's a cool little thing there. And you can't write them, if you want to write them down, you have to compute them, because this is not a closed form expression for them. Yes, Connie, it is. Nice. Most of your classmates did not get that, actually. Yeah, well, we'll do it. Okay, so everyone, I'm going to wrap it up in, let's say, 30. Yeah, remember, this is just the Leibniz notation for take two derivatives of this function. Well, you deal with it using the chain rule, right? Because that's what we're talking about. No, you have to do a little bit of something else, right? The exponent just stays there, but there is this, there's a little something else you have to do. Right, yeah, exactly. Yeah, so maybe that's a good thing, Connie. We'll talk about that first, and we'll just show how to differentiate that function, because we'll use it so many times. Okay, so yeah, let me end it here. All right, overwhelming majority of the class is B. Yeah, it's not B. B is not the correct answer. All right, let's take a look, and we'll see if we can figure out what it is. Now, I haven't worked this out ahead of time. Okay, I promise you, I am being a lazy mathematician, and I have not worked this out ahead of time. I know what the answers are because I have the answer sheet, right? But I'm going to do it for you live, and you can all see, my thought process and how we do it. So we're told the Hermite polynomials are of this form: -1 to the n, e to the x squared, dn dx to the n, e to the -x squared. Okay, and we're asked for h2, right? So we want h2. So just everywhere I see an n equals, or anywhere I see an n, I'm just going to put a 2 in, right? E to the x squared. And then we're going to take the second derivative of e to the -x squared, like that. Okay, so there isn't too much that we have to do here, but what we do have to do is we have to take the second derivative of e to the -x squared, right? That's kind of like the critical thing that we're doing. So let's take a derivative of e to the -x squared. So let's compute d to the dx, or d dx, e to the negative x squared, okay? So I'm thinking of the outer function here. Here, the outer function is e to the x, and the inner function is negative x squared, okay? So what I'm gonna get is e to the negative x squared times the derivative of the inner function, which is negative 2x. Now, if that's bugging anyone, again, feel free to yell out so I can, because I can break that down into more steps if we want. I mean, it's not even more steps. It's just I can define the functions to be called f and g or something, and we can go through it like that. But is everyone okay with this part, or are there? Sure. Okay. So let me maybe phrase this a different way. Let's let f of x be e to the x, and g of x be negative x squared. So e to the negative x squared is f of g of x, right? And exactly, Christian, yeah. Okay, so when I differentiate, that's the same thing as differentiating f of g of x, right? And that's f prime g of x, g prime of x. Okay, so f of x, f prime is equal to f, right? So I'm going to get e to the g of x, and g of x is negative x squared. The derivative of that is negative 2x. And when I plug g of x back in, e to negative x squared times negative 2x, like that. Okay? Ahmed, does that help too? You're okay there? You kind of saw how it works? Okay, cool. Now that's only the first derivative, right? So let me just recall that. So the derivative of e to the negative x squared is, and let me put it on this side, negative 2x e to the negative x squared. Okay, but I have to take two derivatives, right? So now the second derivative of e to the negative x squared is the derivative of its derivative. And now I'm in a situation where I'm going to have to use the product rule, right? So I'm going to have, let me just pull that negative 2 out of everything. Now I'm going to take the derivative of the first. Maybe let me use an even bigger bracket. Derivative of the first times the second plus the second times the derivative, plus the derivative of the second times the first. Like so, okay? And now we don't have to redo this calculation. We already know what this is, right? We know that this is negative 2x e to the negative x squared. We already did that calculation, right? So we can simplify this pretty quickly. The derivative of x is, of course, just equal to 1, right? So we're going to get negative 2 e to the negative x squared minus 2x squared e to the negative x squared, like that. Okay, and if we want, we can, mess around with some minus signs and stuff, maybe pull out an e to the negative x squared. I'm going to put the minus sign inside. That's just going to have the effect of switching around the signs. So we're going to get 2x squared minus 1. I guess I should still have a 2 out here, like so. Okay, so that last step is just me, I put that minus sign outside, I took that thing and I put it inside, and then I factored out an e to the negative x squared from everything. So it's just a little bit of algebra there, nothing serious. But the reason why I want to factor out that e to the negative x squared is, well, we're not done, right? I've now figured out the derivative of e to the negative x squared, but I have to go back, and this is the actual formula for the Hermite polynomial at the top of the screen here, right? So we've got that h2 of x is negative 1 squared e to the x squared d squared dx squared e to the negative x squared. Now we've computed this. Negative 1 squared, this thing is just equal to 1. So we're going to get e to the x squared times 2e to the negative x squared, 2x squared minus 1. That thing cancels that thing. That gives me 2 times 2x squared minus 1, which is 4x squared minus 2. That was option D. Would an f prime g of x be the derivative of e to the x squared in the line after outer inner? Well, I'm not quite certain what you mean, Simon, because, right, remember when you, right, chain rule says you have to do f prime g of x, g prime of x. So I don't know where your g prime went. Yeah, and Brandon, like, what I mean is that, oh, okay, f prime, okay, so f prime of x is equal to e to the x, right? Oh, yeah, no, Saim, you're right. Yeah, f prime g of x is e to the negative x squared. Yeah, that is true. Yeah, this thing right here, that is f prime g of x. And then this thing right here is the g prime of x. So is there a question in there that I missed? But you're right, like that is the f prime g of x. The derivative is this whole thing. No problem, Emma? Well, f prime g of x is the same thing as f of g of x, right? Because f and f prime are the same, right? Because f is the function e to the x, and the derivative of e to the x is the same thing. So yes, right? In that case, f of g of x and f prime of g of x are the same function, precisely because f and f prime are the same function. Ahmed, there's nothing beneath this. That's the bottom. Okay. Let me I want to maybe see if I can get one more in really, really quick. So let me zoom back in on this. And let's pop, which one do we want to do? What, go away. Okay. Yeah, let's do this one. Oh, that's what it is. This should be browse. There we go. All right, let's try this one. This is probably more like the sort of thing you might see on I mean, that previous question is nice because it's, you know, it's Wolfram Alphabet, but it's not as obvious. This one is pretty nice too. Let's see if you can sort that one
out. While that's happening, I'm probably gonna have that start the tutorial. So
okay,
I'm gonna leave you to it.
All right, see you later.
See ya.
Good advice to get rid of brain fog. I suppose it depends on how your brain fog is forming. I mean, the number one way is getting a good night's rest, right? I think as students, we sometimes push ourselves too far and don't sleep very well. Some students even brag about not sleeping very well, but it's very easy to get brain fog just from not getting enough sleep, right? Sleep is so important as a student. So that's kind of my first way I'd recommend. Yes, Connie, it is. Yeah. Yep, see that? Drink hydrogen. Yeah, I'm not 100% certain what effect that would have on you. Yeah, water is definitely always a good choice, right? Dehydration especially can definitely affect the brain. Yeah. One thing too, yes, definitely. Yeah, water is the superior drink. Another thing too is, especially if you start to become frustrated, if your brain fog is because like you find yourself being frustrated, and I think I've said this before, but like go for a walk. Like I know that it's okay, sure. So you're having trouble, maybe you're having trouble turning off your brain, Ahmed, and this is totally a thing. And I've had this problem too. I always used to have this problem, especially before tests, which is not good the night before a test, right? If you can't sleep. I think it is important to get into like a nightly ritual. This is something that, you know, I will admit affects me as an adult. I have to stop doing stuff an hour or two before I go to bed, right? And I just have to try and relax. So, you know, I put away my work if I'm working in the evening, or I try not to like do too much gaming or anything like that. And I generally just like maybe, you know, don't eat right before bed. That's generally bad. Your body's pumping stuff off. Obviously, don't ingest caffeine or any energy drinks or anything like that. So give yourself an hour or two before bed in that case. Go maybe like read a book for fun. Don't, not like a textbook. Go read a book for fun. Help your brain sort of shut down, turn off. Yeah, sure. Listen to soft music. You know, and just generally get into a habit of training yourself that when I do these things, right, first of all, that you're turning your brain off, you're just trying to put yourself into a relaxation state before you go to bed. And then as well, the more you do this, and if you get into a habit, you say, yeah, maybe, but as you get into a habit, you're actually training your body that when it sees these signals that it is time to sleep, right? Yeah, so Ahmed, you actually could have maybe pushed yourself too far, and you've kind of like experienced some burnout as a result of that. Burnout, you just have to pull back from the subject. Reading week might be a good opportunity for you to like recover from that, but you have to, you know, you don't want to burn yourself out too much. It's the same sort of thing. Like even if you're an athlete, you can overtrain, right? So you got to pull back sometimes. Try and really manage your work, assign yourself a certain number of hours every day. I found that I was very productive when I really would schedule myself very tightly into a day. I'd be like, okay, these hours I'm going to spend doing this course, and then I have this lecture, and then these hours I'm going to do this course, and then I'm going to take a break. And you have to schedule yourself breaks, right? You have to make sure you take some time off. I mean, if you're not taking breaks, that could be part of your brain fog as well, right? Like breaks are critical. They're absolutely, absolutely critical. Don't try and do something 8 to 16 hours a day. You're just gonna, you know, yeah, exactly. As well, give yourself extra time. You know, however much you budget, you're definitely gonna go over. I can't emphasize enough breaks. When I used to study for exams, this technique has a name, but I don't know what it is. But I would, I'd study for an hour, and then I'd take a 15-minute break, and then I'd study for an hour. Okay, yeah, sure. Yeah, that sounds about right. So Simon, thank you very much. And so like, and that way I could do that all day, right? With that sort of thing. And what I would do is at the time, like NHL 07 or something came out. And so you could play a game in like 15 minutes. And so I'd study for an hour, and then I'd play a game of like NHL 07 or something. And then when that game was done, I would go back. And that's how I relaxed, because it was just kind of like a mindless thing I didn't need to think about. And it was time limited, right? Like I knew exactly how long my breaks were. So that's, yeah. And part of that is you're just going to have to get into a habit, right? If you can force yourself to get into a habit, then you'll be fine. Cooper Tap, back in the day, I actually used to play that on PC. I played it fairly extensively on the Xbox, but I mean, I haven't really console gamed in many years now. Okay, yeah, creative. That helps. There's lots of things out there, and I think, you know, as much as we all have advice, and Karina's got some great advice, and Saim's got some great advice, and I've got some great advice, and you got to play with everything until you find the thing that works for you, right? Like, I don't think that there's this sort of panacea, one solution is going to fit all. You've got to try a bunch of different things and keep some of the things that work well for you, and throw out some other things until you find something that really gels with your lifestyle and what you want to do. And then once you find it, you're gold, right? Like your money, nothing will stop you. It's the same thing with like your study habits. Like the way I study, the way Karina studies, the way Gurpratap studies, like we're all going to study in different ways. And, the way I study might not be good for you. So you've got to play with it and take what other people are doing and see what works and see what doesn't work, and then figure it out, like what the right thing for you is. And, so much of the difference, I think, if you all ask, we'll take this question up in a second. I think when you all ask fourth year students, a lot of students will say, hey, is fourth year harder or easier than first year? They say, well, it's obviously harder, but you do better. And in no small part of that is because by the time you get to fourth year, you're all pros, right? You're pros because you know how to study, you know how to take breaks and stuff like that. And first year is rough because you're trying to figure that stuff out, right? And you just got to grind through that because that's the way it is, right? Ahmed, yeah, I think everyone's saying that is, that's totally fine. I don't, university isn't about training you for a particular job. It's about training your brain to think. And, when you go out there in the real world, like you're going to find that 90% of the crap that you learned here, you're not going to need. But hopefully what you did learn here is how to think and how to learn and how to apply your knowledge. And then when you get a job, they're going to teach you how to do that job. And what your university education will hopefully do is teach you how to excel in that, right? Like how to develop good habits and how to think abstractly or problem solve, or even just telling you where to look for information can be a useful thing, right? Unless you're doing a professional degree, med school, lawyer, something like that, it's okay to not know what you're going to do. That's totally fine, right? And who knows what's going to happen in a couple of years, right? Are we still going to be in COVID? Like what's going on? Like nobody knows, right? Okay. So let's take up this one. The class said D. That's phenomenal. I love to see this. Yes. And yeah, D is absolutely the correct answer. So good job. Now let's talk about why. So this is question 4 here. So question 4. And actually, you know what? I have a thing too about like career-wise. I'll tell you about when I've done this. Okay, so our function, we've got this thing. So we've got f of x cubed cubed, right? So really there's 3 functions here, right? Everyone, I don't know if you can see it. There's 3 functions. There's the x cubed that's inside the f, right? That's the first function. There's another function, which is the f itself. That's another function. And then you're cubing everything. So that's a third function, right? So there's 3 functions here. Okay, so just to make things clear, let's give the cubing function a name. Let's maybe call that g, right? So let's say let g of x be equal to x cubed, okay? Exactly, yeah, f of x cubed is a composite function, right? Because it's not just f of x, right? It's not just the x inside, it's actually x cubed. So there is that sort of composite inside, and we have to treat that a little bit differently. So if I were to write this whole thing now as a function, it's actually g of f of g of x. Right? Do we all see that? That might, if that's a jump, let me know, but this function is g of f of g of x. So it's a 3-fold composite of functions. It's just the same function has to happen to be used twice. Right, so that outside composite, so this outside g is, here, let me put it in yellow. That's this part, right? Because then you cube everything. So that's that part. The f of x is just the f of x. And then maybe let me do like this in blue or something. That's the, like that. right? So the blue x cubed in the inside, that's a g of x. I think we're all okay with that. Then you've got the f of x cubed. Okay, no problem. But the yellow part is the x cubed on the outside. Are the blue and yellow g, they're the same function, but they occur at different places, right? Like one of the functions is the outermost function, one of them is the innermost, but they are the same function. They're both just the cubing function. So what if both were 4, or Curdy, are you changing a particular one? Like just one of them? Okay, well, why don't we do that one after? So like, let's do this one first, and then we can change one of them to a 4, and we can see how that would be different. But yeah, we would actually have a different function in that case. Okay, so we're going to differentiate this function now. Now, does everyone remember how do you differentiate 3 functions? I think I explicitly say this in the video, but maybe this is worth, talking about again. So maybe as an aside, how do you differentiate 3 or more function? And by this, I mean a composition, right? Exactly, Saim. That's exactly what you would do. And Curdy, you could kind of do it that way as well. It kind of all depends on how we want to like smush together the chain. I did chain into power. Yeah, absolutely. Nimir, that's phenomenal. You can do it that way. So you can definitely like break it into pieces. Now, at the end of the day, it does kind of follow. You remember when we were talking about differentiating 3 or more products, and I told you that there was this kind of slick thing. Now, for those of you who see what to do, that's phenomenal. I don't want to take away from what you've done. You've all done a great job. But what I want to do is show you a little pattern that can just make your life a little bit easier too. So let's say I'm going to call these f of g of h of x, okay? And these functions are not related to the actual question, right? These are just 3 new functions arbitrarily. So the way I think of these is as matryoshka dolls. Does anyone know what matryoshka dolls are? I don't know if I said that explicitly in my video, but I always think about these as matryoshka dolls. Yeah, those Russian things. Does everyone like the Russian nesting dolls? Do you know where you have like the big doll and then you open it up and then inside there's another little doll and you open it up, right? So it's the Russian nesting dolls, right? Those are matryoshka dolls. So to me, f of g of h of x, right? This thing is a matryoshka doll, right? There's this big outer function f, and inside of it there's a g, and inside of it there's an h. So when we do the chain rule, to me, this looks like a matryoshka doll. So what I do is I differentiate the outside, and sure, whatever, you always have to evaluate at the inside. And then I take the inside function and I bring it out, right? And then I differentiate the g, and then I take the inside function out and I differentiate the h. Do you see what I'm saying here? Like to kind of see that matryoshka thing. I always just keep taking the inside function out and then I slap a derivative on the outside and then take the inside function out, slap a derivative on outside, inside function out, slap a derivative. And if you keep doing that, you'll always get the right answer. Okay. It turns out that this always works. Usually you want to kind of push, like it ultimately doesn't matter, Amit. So in your terms of questions, obviously I could have written h prime first and then g prime and then f prime. That really doesn't make a difference. But for the matryoshka doll model, if you want to think about it like that, I think I usually maybe think about it as doing outside and then taking the inside out and then differentiating and doing it like that. If you want to kind of think about it in the opposite direction, I don't think there's anything wrong with that. It's not how I think about it. But I mean, if you get the same formula, then yeah, that's totally fine. Like when you take the inner function out, you would have the derivative for that inner function right away, right? Yeah, exactly. So Kelly, you're right. When I say I'm taking it out, what I mean is I'm taking it out and then I'm differentiating it, right? And so, this pattern just continues. If I had 4 functions, if I differentiated, now I need to name 4 functions. Let's maybe call it K. We'll call it K for Kelly. And right, you still just have, now there's too many parentheses now, right? But g prime of h of k of x times h prime of k of x times k prime of x. Right? So as soon as when we take the inside function out, we have to throw a derivative on that, but we just keep Matryoshka dolling it out until we run out of inside functions, right? And Ahmed, like, I don't know if you're inside differentiate the inner function, most thing works here, but like if your kind of idea is consistent with both of the things that I've written down here, then you're fine, right? Then you're in a good place. Okay, so this is how I think about it. This will always work because what you're actually doing here is this idea of treating, G composed H as a single function. That is effectively what we're doing when we Matryoshka doll it out. But maybe this pattern will help you think about things and help you do some computations. I think it's quite nice. Okay, so that's our aside. Now, if we go back to the original function, okay, so we're trying to differentiate G of F of G of X, right? So I'm just going to Matryoshka it out of G of X times F prime of G of X times G prime of X, right? Everyone hopefully agrees. Yeah, we're in office hours now. Hopefully, Ahmed, you didn't have to run and you're not like late for a tutorial or something. But okay, so I've just Matryoshka out. Okay, good. So I've done our little Matryoshka trick. Now, remember, G of X up here is X cubed. So let me just, while I'm at it, let's just write down what G prime of X is, right? G prime of X is 3X squared. Okay, so I'm going to plug that in here. So I'm going to get 3 times F of G of X cubed, right? That's just me plugging those in. All right, see you same. So that's me evaluating that G prime times F prime of G of X times G prime of X, which is 3X squared, right? And again, let's start plugging in more G's. We don't know what F is. Oh, yeah, sorry. Yeah, that should be squared. Thank you. Thank you. Okay, and let's just plug in the rest of the G's. So we're going to get 3 times F of X cubed all squared times, like I said, we don't know anything about F prime, so we kind of have to just leave it the way it is, times 3X squared. And that is answer D. Right? So hopefully everyone, like if you're struggling with this sort of stuff, the lesson to take from this is to really break this down into parts, right? Like if you can't do it in your head, if you can do it in your head, great. But if you can't do it in your head, break it down, actually explicitly give names to the functions and try and do it like that. Now, Curdy asked, well, what happens if one of them is a 4? So let's say, what do you want? The inside function to be a 4, or do you want the outside function to be a 4? So what if we change a number? Outside, okay. So we have something like F of X cubed to the power of 4. So in this case, let's say maybe G of X is X cubed. Now, when we raise something to the power of 4, we have to give it a new name because it's a different function, right? So now this thing is equal to H of F of G, which is maybe a weird order of functions, but that's okay, right? And so when we differentiate it, we would get H prime F G of X times F prime G of X times G prime of X. Again, we know G prime of X up here is 3X squared. We know H prime of X is 4X cubed. So we plug this in, we get 4 F of X cubed times F prime of X cubed times 3X squared, like that, right? And if you want, right, practice this, you could do something like, well, what is the derivative of, right? The next, I hope, step that you would do is say, what is the derivative of this thing? And see if you can do it, because it's not that much harder, right? It's basically the same sort of math, but change these numbers around, and then even best case scenario is do the abstract version of this question like so. Yeah, no problem. All right, so that takes care of the pool questions. I don't think there's really too much more I want to do. We will talk about like logarithmic differentiation later, probably on Thursday. We're in office hours now, though. Oh, I guess, Ahmed, let me answer sort of thing about that career thing. And for the rest of you who have math questions, queue them up and I'll happy to take a look at them. A9Q1, okay. And yeah, so when I finished my undergrad, I didn't know what I wanted to do, right? I was interested in pursuing grad school. So I applied, right? I applied for some grad schools. I also had, there were a couple of development, like software development companies. Oh, Doug, yeah, somebody else asked the same thing. Yeah, okay, everyone's asking the same sort of question, so we can do that. So I'm gonna pull it up and then I'll tell you my story. So I had a bunch of software development companies that were looking at me. I didn't really want to go be a code monkey though, so I wasn't super interested in that. And I was thinking actually about the Canadian Armed Forces, believe it or not. Like I was legitimately thinking about doing that. And then I was thinking about grad school, and ultimately I went to grad school. And then when I finished my master's degree, I was again thinking about the armed forces. Apparently that was the thing I was thinking about a lot. I got a job to go make aircraft, like design jet fighters. So I was offered a job doing that as part of like a PhD, or go to grad school. So you can see that there were multiple points in my career where I wasn't certain what I wanted to do. And then after my PhD, what was I going to do? Like, was I going to go into finance, management consulting, software development, right? Like, what was I going to do? Brandon, what do you mean with a math degree? Designing jet planes? Yeah, that's cool, eh? I had an engineering professor approach me and said, I know you're a mathematician, but we want you to do your PhD in engineering. And we want you to do it with us because we need a mathematician, because the like modern day, especially again, there's some ethical implications about working on, weapons, obviously. But modern day, like stealth fighters, for example, are not aerodynamic, right? They're not meant to fly. So you constantly have you have to do a lot of mathematics in order to keep those things in the air. And basically, if their control systems shut down, they just plunge out of the air because they can't glide. They're so not aerodynamic. And so, yeah, math degree can do that. Let me tell you, there was this really cool, you know what? I actually have a question like this assignment question. I was at this conference and there's this guy working for the US Navy, and he did this like really cool project. And what he did is there were two boats, right? And one of the boats had a big crane on it. And because you're trying to move, right? You're trying to resupply in the ocean. So you're trying to resupply one ship from another. And so you've got a crane on one boat and it's trying to pick up supplies on another boat, right? This is hard to do because guess what? The ocean is not particularly still. So he, again, mathematically, and then he implemented it, and it was super cool, figured out how you could actually stabilize the crane arm in order to pick up cargo from one ship and put it on another. And what he was able to demonstrate is you could actually put a wrecking ball in one end of the crane and have a person stand on the other end of the crane in choppy waters and basically revolve that wrecking ball within a foot of that person and never hit him. And he was able to design this mathematically, which I thought was super, super cool. There are other things like, I'm trying to simultaneously tell the story and find what I'm looking for. Yeah, there are other things like traffic analysis. That's all mathematics, right? It's discrete wave theory. So that's all mathematics. Like there's tons of really cool stuff you can do with a math degree. Like logistics is all math. I think it's the next one. Yeah, here we go. I mean, yeah, there's all sorts of things that you can do. For example, like the cruise control in your car, that's all math, right? Like all that stuff is mathematics. Also, like, let alone if you want to do stuff like send rockets to the moon, all that stuff is math, right? There's so much cool stuff that math does in your everyday life. Your ability of your phone to like send and receive signals is all math, right? When you use the internet and you all can see like my image on the screen, there's tons of like compression and data compression and security. That's all math. Everything is math, like high-end complicated math. I mean, that's not why I study math, but like I love math. I actually did a lot of applied mathematics, but you know, that being said, yeah, it's all math. And there's a lot of really cool stuff you can do out there that isn't just like quantitative finance and stuff, right? Which of course you can also do. Okay, so here, let's try the following. So let's say I give you a function, here's say -1, here's say 1. And let's say I do something similar. I tell you the function is, well, here, maybe let's do something different. So let's say the function is -1, and then it becomes +1. Like this. Okay, so you're told f of x is equal to -1 if x is less than 1, f of x equals +1 if x is greater than 1. Okay, so this is similar to the assignment, right? And you have to figure out what you're going to do between -1 and 1. Okay, so the assignment question first says, all right, do it in such a way that the function is continuous. So could someone tell me what could I do to make this function continuous? That's the only restriction. It's just that it's continuous. Yeah, sure. Yeah, and Sean, that's exactly the same thing. And Brandon happened to write that as an equation. Yeah, the limits of both sides have to be equal. But alternative, Kelly, just from an intuitive viewpoint, all we need to really do is just make sure that these things touch each other, right? Like this. Does everyone agree that works? Yeah, and Brandon kind of gives us that equation, right? F of x is equal to x. Now, this function is not differentiable, though, right? This function not differentiable here. Okay, because it's got that like, you know, differentiable functions have to be nice and smooth. They don't have corners or jagged edges or anything like that. So this is a continuous solution to this problem, but it's not a differentiable one, okay? So let's say I had said, find a differentiable one. And let's say in particular that I forced it to be cubic. And this is maybe a boring example because it's in some sense obvious what the solution is, but now let's make a differentiable solution. So suppose C3x cubed plus C2x squared plus C1x plus C naught. Let's make it differentiable. So we've got a couple of things that we need to ask ourselves. We've got four variables, right? Or 4 constants we need to figure out. We need to figure out C0, C1, C2, and C3. So what that means is we need to impose 4 restrictions. What are those restrictions? What are a couple of things that we can immediately think must be true? So for F to be C3 can't, that's true, Brandon, but let's not worry about it in terms of that just yet. Let's just think about like, what must be true about the function F? So first of all, does F still need to be continuous? If I tell you this thing needs to be differentiable, does it also need to be continuous? Does anyone remember the answer to this? Right, okay, yeah, because we know differentiable functions are continuous. So if my function, whatever it looks like, I'm just going to make something up here. Maybe it looks something like that, right? I am going to demand that this has to be equal, right? The limits here have to be equal. And in fact, because it's continuous, we don't even have to take limits. What is this condition? I'm saying that F has to be equal to what at -1? -1. Does everyone agree? Like the function, whatever I draw, it actually has to go into here, right? It can't do this. That's not allowed, right? It can't like shoot off to infinity. That's not allowed. Whatever I draw has to actually touch that point. So that's a restriction that f of -1 has to be -1. Okay. So What is it? Okay, well, no, but let's not worry about that yet, Jeremiah, right? So what's another condition? So if we do the same thing at the other endpoint, what's the condition over here for continuity? What's that restriction? F of 1 equals 1, perfect. Okay, does everyone agree? Like whatever this does, again, over here, it has to actually touch. Everyone's good? No one's upset about that? Okay. Now, fine, that's great. That's the continuity condition, but it doesn't give us the differentiability condition. So what I need over here now as well is I can't just shoot off like this, right? Like I can't have a jagged edge. Whatever I do, it has to be, it has to be smooth like, right? It has to be kind of smooth. So what is the derivative? Let's look at the blue thing. What's the derivative at -1 or as I approach -1? If I look at this function, what is its derivative? Kelly, because that's the condition, right? Like we're doing the case where the function has to be, or maybe you're asking, why does differentiable have to be smooth? Basically, if you have anything that looks like this, then the tangent lines don't agree, right? Like you have on the left-hand side, your tangent wants to look like this. And on the right-hand side, your tangent wants to look like this. And so if you have any of those corners, you won't have a single tangent line. So it doesn't know what it wants to do. So as a result, it kind of has to move very kind of nice and smooth. That's just an intuitive sort of idea, right? Dowd, yes, yeah, exactly. 1.1 is just continuous. Right, okay, so everyone agrees, right? The derivative of this function is 0. So if f is going to, like f has to have the same derivative at this point. For when I glue this function f in, right, it has to have the same derivative there. So what's this condition? What's the current condition on f prime of -1? It also has to be 0, right? And so same thing for the other side. What's f prime of 1? Also has to be 0. Okay. So does everyone see how I set that up? Right? You just kind of ask yourself, like, what things do I know need to be true? So now what I'm going to do is I'm going to take these and I'm going to plug them into f, right? We know that f looks like this. And we know f prime is what? 3c3x squared plus 2c2x plus c1. So let's figure out what these is. So I'm going to call these equation 1, equation 2, equation 3, and equation 4. So equation 1 is -c3 plus c2 minus c1 plus c0 equals -1. After this, could you repeat how we know there's 0? Okay, no, Jack, yeah, sure. So the derivative, if you look at the derivative at this point, is 0, right? The tangent line is always just, at this point, is just horizontal. So whatever I glue in also kind of has to start off horizontal, right? It can't do something like that. It's got to start off horizontal because their derivatives have to be the same. Yeah. So if this line, right, instead of being horizontal had looked something like this, then the green thing would have had to do the same thing, right? It would have had to just at least start off pointing in the same direction. Okay, hold on. Let me just fix the graph here. Okay. Yeah, no problem. So Curdy, what I did for this here, maybe let me write this in a different way. So this is, I said, we're going to take this equation. So I got -1 is f of -1. And then I'm going to plug that into this equation here, right? So I'm going to get c3 times -1 cubed plus c2 times -1 squared plus c1 times -1 plus c0. And that's -c3 plus c2 minus c1 plus c0. Okay, good. Yeah, no, I like that. That's good. Okay, and you're going to do that for all of them, right? So if we do that for equation 2, we get that 0 is 3c3 minus 2c2 plus c1, right? So wait, so now we have 4 equations because we have 2 normal equations, 2 derivatives, and 4 variables. So we just use some sort of linear algebra. Yes, exactly. So if you do this, you are going to get 4 equations, you are going to get 4 unknowns, and you all know how to solve that, right? Because set up a matrix, plug it into octave, row reduce it, and solve for your constants, or solve for your coefficients. Does that make sense? All right, so you would just keep going. Like if yeah, exactly, right? It never goes away. If we did equation 3, this would be 1 is equal to C3 plus C2 plus C1 plus C0. And then equation 4 is 0 is equal to 3C3 plus 2C2 plus C1. You have, yeah, good. Yeah, no, I'm happy. So you have 4 equations and 4 unknowns. Go solve it. I'm pretty sure the solution is all of them are 0 except for C3, which is 1. I'm pretty sure this is the solution, but go plug it into octave for me. And I'm pretty sure that's the answer. Oh, that doesn't actually satisfy equation 2 though, does it? Well, you guys go plug that in and tell me what you get. Okay, so Kelly, can you tell me what's bugging you? Like what went wrong? Is it how did I get these equations? Okay, here, let's try 3. Okay, so I'm gonna erase 3 and let's do 3 again. So equation 3 is this one right here, right? So I know that 1 is equal to f of 1, right? And f is the blue highlighted thing in the, see Ahmed? It's the blue highlighted thing in the top right-hand corner. So if I plug 1 into this thing right here, right? Then that's gonna be C3 times 1 cubed plus C2 times 1 squared plus C1 times 1 plus C0. And then if you just actually solve for those, like, evaluate what 1 cubed is, you get that thing. Jeremiah, you're given this as part of you're given what f of x is as part of the question. Just like if you look at assignment 9, question 1.2, it says, suppose that f of x is C4 x to the 4 plus blah, 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 blah. So Kelly, does that make sense now? Do you see where that equation come from? Equation 3, though, is not the derivative equation, right? Equation 4 is the derivative equation. So yeah, so when I did equation 4, I did do f prime of 1. So I plugged 1 into this thing, and that's how I got it. Okay, sweet. So Brandon solved it and got C1 is 3/2, C3 is -1/2, and the rest were 0. Oops, shoot. Okay, and here, let's plot that. Let's see if that works. The derivative is 0 because the derivative of all the numbers are 0. The derivative is 0 because these blue things all have derivative of 0. Oops, I erased that blue thing. These blue things all have a derivative of 0 at plus and minus 1, right? So that's why the derivative there was 0, Jeremiah. Okay, let's plot this. Let's see if this works. And let's see if Brandon correctly solved this linear system. Firefox, what are you doing? Of course it's installing updates. What are you doing, Firefox? Let's go. Okay. Yes. It's recording and screen sharing, so we'll give it a break. Okay, so let's see if it works. So what did you say? You said C3, so it should be -1/2. No, that's an x cubed plus 3/2 x. Yeah, that seems to work, right? How do we do piecewise functions in octave again? Or in Desmos? It's got some sort of weird, yeah. Oop, why do I keep doing that? It's got some sort of weird thing. Okay, yeah, so it's like, so -1 less than or equal to x less than or equal to 1, like this. And then x less than -1 is just -1. Wait, what did I? Oh, colon. And x greater than 1 is 1. Right? And so voila, hopefully you all see. So this thing is continuous, right? And it looks to be differentiable too, right? Like if we zoom in here, maybe let me zoom in further. Notice how there's no like weird jagged edges or anything. It just kind of like comes in really, really smoothly. And that's exactly what we were trying to do. So we solved this problem, right? This was the answer that we got if we solved those 4 equations and 4 unknowns. And that's how we get our answer, right? And so that's how we do it. So Kelly, the fractions came from like just solving the system, right? So here, let's do some like Octave Online stuff. What was it? Was it called like Octave Online? There we go. Okay, A is equal to, I don't remember what my equations are. Here, let's maybe put this over here, and let's put this over here. So A is, man, I can't see anything. My screen is too small. Zoom out. And then stupid Zoom is in the way. Okay. So we've got 1, -1, 1, -1, -1, 1, -2, 3, oh, sorry, 0, 1, -2, 3, 0, 1, 1, 1, 1, 1, and then 0, 1, 2, 3, 0. Right, and there we go. That's where our fractions are, right? So 3/2 and -1/2. Yeah, right. So you use the equation, or you use the quartic that you're given, set up a system of equations, and use those system of equations to figure out what the coefficients should be, and then you're good to go. Okay, A9Q2, sure. Here, let me just try to make this big again. To get the matrix values input, you just plugged in the value into the equation. Right, yeah, exactly. Yeah, I just plugged it into the equation. Okay, sure. For question 2, let's see. It's hard to do something similar. Yeah. So it's for assignment, question 2 of the assignment. Okay, yeah, let's do something like this. So let's say I gave you, I have no idea if this is going to work. Okay, I'm just making something up off the top of my head. So let's say I took the function y is equal to 1 over x, or f of x equals 1 over x. but I really want the tangent. Okay, let's do something similar, but I'm going to make you all do the work. Okay, I'm not doing any work. So I'm going to give you a similar problem. So f of x equals 1 over x. Okay, and I want, so same sort of situation. So I want the triangle formed by the xy axes and the tangent line. So look at the triangle formed by x, y axes and the tangent line. Let's say x has to be greater than 0 as well. Okay, right? So find the point where the triangle has area 4. Okay. So what we're saying here, let me kind of graph this for you. Here's y equals 1 over x, right? And if you give some point, let's say A, and you draw the tangent line to this point, it looks something like this. And what I want you to do is compute the area of this triangle and tell me for what value of A is this triangle equal to, is the area of this triangle equal to 4? Okay, and hopefully you can visualize it. If you actually move the point A around, it's going to change the triangle, right? And so actually, I think there should probably be 2 values of A for which you get a triangle of area 4. But yeah, we'll see. 4 might be too big. We might need to choose a smaller number. So does everyone see it? So base times height has to be equal to 8. Sure. Base B and H is just the X and Y values though, right? Exactly, exactly. So what you need to do, right, is the area of the triangle is base times height divided by 2. Here's the base, right? The base is the x-intercept, but you have to figure out what that is as a function of A, right? Because as you move A around, that x-intercept is going to be different. And then here's the height, right? But it also is going to depend on A. As you move A around, the height is going to change as well. So you've got this, B of A times H of A divided by 2 has to equal to 4. And you want to solve that for A. Now, to figure out what B of A and H of A are, you just need to figure out the equation of this tangent line. And once you know the equation of that tangent line, I think you all know how to find X and Y intercepts, right? Like if Y equals mx plus B, right? B is the y-intercept. And then to get the x-intercept, you plug in 0 and solve for x, right? So it'd be like negative b over m or something like that. So does that make sense on what you're supposed to do? Yeah, find the derivative of the function, use it to find the equation of the tangent line and go from there. Kelly, specifically, can you tell me like what part of the triangle you don't get? So will the derivative of y be the equation of our tangent? The derivative of y will give you the slope of the tangent. But to get the equation of the tangent, you need a little bit. Yeah, you need a little bit more. But yeah, exactly. The slope of the tangent is the derivative of the function at the point A. And actually, maybe I can. So it's not, I mean, like here, let's try it. Let's choose a value of A. So let's say we choose A is equal to 1. Okay, and let's do the calculation. So if A is equal to 1, f prime of x is negative 1 over x squared. So f prime of 1 is equal to negative 1. right? So it's telling me the slope of the equation, or the slope of the tangent line is equal to -1. Now I know that this passes through the point 1, 1, right? Because that's on this line. So by the point slope formula, I would have the equation of the tangent line is y minus 1 is equal to x minus, what do I want? So I want -1 times x minus 1. So y is equal to -x plus 2. Okay, so this line here now has the equation -x plus 2, right? So the y-intercept, the height of this triangle is 2, and the x-intercept is also 2. So the equation of this this triangle has area 2. Okay, the number 2 showed up too many times, right? But so the area here is equal to 2. Now, if I change it, if I move, so all of that I was able to do because I set a is equal to 1. If I set a was equal to 2 instead, or let's say a is equal to 3/2, I get a different triangle, right? And that triangle is going to have a different area. And if I set a is equal to like negative, or a is equal to 1/2, I get a different triangle. And so what I'm trying to do is figure out which value of a gives a triangle. Yeah, exactly. I'm just testing different values. And so I'm just trying to find the value of a that gives me the right area, right? But the point is not to guess, right? So here I just did an example where a was equal to 1. Why not leave a as just being a, right? So don't solve it explicitly, just leave it as a. Do all of these calculations that I did, but everywhere there's a 1, you put an a instead. And at the end of the day, you'll get an equation that only has a's in it. And from that equation, you'll be able to figure out the final answer. Does that make sense? It might be if the answer ended up being constant for this equation, it would be crazy. But if it is, that's awesome. But it might have accidentally worked out to be constant. And if it is, we found a great exercise problem. Yes, actually it is constant. So Ariana, yes, the area this is actually a fluky example. This is a bad example because the area is always equal to 2. And that is unusual though. Normally that doesn't happen. This is a special property of the function y equals 1 over x. But yeah, Ariana, assuming you actually ran through the calculation, the area is always exactly 2. Yeah. And I just checked it. I do actually have this on another assignment. So. Yeah, in this case, it's funny that it just ended up kind of canceling out to always give you the same area. Yeah, and exactly. And Kelly, if it doesn't make sense, throw something on Piazza. We're happy to help there as well. See how much progress you can make on it. And yeah, here's another thing. So Ariana has kind of pointed out that the area for this problem that I've set up, the area is actually constant. So see if you can derive that, right? Like if you want to mess around with this particular problem, see if you can show that the area is always exactly equal to 2. That won't be true for the question that we gave you on the assignment, but it is true for this one. Kind of. Brandon, yes, I would say though, just be a little bit careful. Maybe use something else for x, like let x be a or something, just so you're not kind of conflating things here. Because no, I think you're okay. Then we can solve for this by doing this. That's not true though. Your last equation there isn't quite right, right? So you've got that, the function passes through the point x 1 over x, right? And then therefore that 1 over x must be equal to m times x plus b, right? So you dropped this when you did it. Yeah. But yeah, otherwise you're fine. Yeah. And Curdy, yes, this is very similar to that. Okay, and Theodore, I don't know if you've already left, but see you later. See you, Christian. Okay, see you, Kelly. Okay, anyone else? Anything else? Nothing? Will there be a lot of derivatives on the fifth test? I mean, yeah, the fifth test is probably going to be all differentiation. So yeah, that's probably a fair. Why, you don't like derivatives? And Brandon, sure, what's up?
Is it fine if I talk?
Sure.
I'd ask it like speaking, but at the same time you're recording, and I don't really feel comfortable saying it while you're recording. Right, I'm not sure if.
Let me unrecord. I'm sure nobody cares if the last 5 minutes of this thing is not.
That's fair.